learn? Try. Okay. If you have SPSS installed in your laptop, you could have practiced so that you retain. Otherwise, so how many of you, be honest, how many of you understood when the non-parametric was explained? I'm telling you the calculation part.
Calculation part was not discussed.
Application is different. For what data, what test you are using is one thing. And some of the slides were shown, even I was observing, that are calculations, how the ranks are taken, how it is calculated. He even told you not to look at the formula. Okay, that's what our SPSS does. But the only thing is that you should know exactly. That's what the in the previous session the core point is that you should know where this test to be used. What is normal distribution? And why and where these tests to be used, whether the data is fit for a parametric test or non-parametric test, and appropriately it should be used. That's all. So yesterday what we have done, I just recap in 5 minutes. We started from basic, entering a data, preparing a master data set in Excel, importing them into SPSS, defining the variables like numerical, giving values, missing values, all these things. Then we did some exercise related to split the data, selection of data, sorting the data, the way you wanted to organize. For example, yesterday you might have not related why I have to use sorting the data. Today you seen the if you are manually doing, of course you don't need to sort data. When you do, if you are doing a Mann-Whitney or Wilcoxon rank sum test, just shown the ranks of each of the observation to be taken, then the group has to be divided and their original rank has to be calculated in total. That's why Wilcoxon rank sum test. For that you have to organize the data into ascending order to assign the rank. Right? If you do manually in Excel, you have to organize that particular column into ascending order, then next sheet you will put a rank, then you will calculate. Okay. If you are doing it in SPSS, you don't need to even organize it in, sort it into the rank. When you apply the test, it automatically calculate all these it will give you only the output. What is the mean rank of this group, what is the mean rank of the other group, what is the p-value, everything it comes out. But if sorting is necessary for ranking manually, you have to sort. That's why that sort functions uses. So we three functions we mainly commonly use as we have discussed yesterday: sorting, selection, and split. Split is required sometime when you do a subgroup analysis. Then we have seen computation option, transfer data. Right? Transfer, then you can compute one variable to other variable, and recode into different variables. That option you can see that when the transform comes down, then recode into different variables. Which data we recoded yesterday? Do you remember the data variable which we have recoded? BMI. We calculated BMI from height and weight. Then we recoded that into underweight, normal weight, overweight, and obesity. You remember, right? Then we did a descriptive statistics, calculating mean, median, mode, minimum, maximum, range, interquartile ranges, 25th percentile, 50th percentile, 75th percentile. All these with one single window, all these possible. Then frequency and percentages, a basic descriptive statistic. Also we have seen how do you do correlation, right? Pearson correlation, when the both observations are normally distributed. Also we have seen how to prepare a scatter plot diagram, right? For correlation, whenever you do a correlation, how do you do a scatter plot diagram? Then we move on to compare the means. When we move, light to be switched off, this light to be off. They want to sleep, I think. Yeah. Joking. Yes. This is cinema theater effect. No, not this much. They are already dozing off, and you put off the light, and it's good. No, I think we need little more light.
Yes.
Very dark, no,
Yes.
very dark, and I don't feel like. I'm not a drama artist, and the blank face like this. Then I understand. I'm going. What I'm saying is going out of your
mind.
head. So it is always, as a teacher, I want to observe your face whenever I teach. It's not you are sitting in the dark. Little more light is required. Sample t-test, and we did a pad t-test comparing pre-test and post-test, that is repeated measures. The same thing, only today it was all non-parametric was shown to you, just a replacement of these. If it is parametric, you will use independent sample t-test. If it is non-parametric, you will use Mann-Whitney u-test or Wilcoxon rank sum test, right? If here you will do a paired t-test, there you will do a signed rank sum test. So it is just like a alternate. So if you understand parametric, you will understand what to be applied in the non-parametric. Okay.
इसको बंद कर देना. ठीक.
So today with the non-parametric, first of all, the commonly used chi-square test. We'll see Mann-Whitney U test, and then we also try signed rank sum test. Okay, for repeated classes.
So last class we left with ANOVA, one-way ANOVA.
One-way ANOVA is still left. Yes. I think I have prepared one data for that. I have prepared another data. It is just a mock data. I have added designation. Okay, that is designation in the sense we can call it as a instead of designation. Okay, designation also fine. We have three levels of designation: PG student, BSc student, and post basic students. And we are going to do an analysis with the online interest class. This is usually this is a non-parametric distribution. It's a kind of a rank. Already it is a kind of rank data. So we are going to compare these, whether the interest in attending online classes is same or different between these three groups. Yesterday we have compared weight of urban and rural. That means we compared the two groups, two independent groups. Now we have three groups. If there are two groups, you require only independent sample t-test. If there are three groups, then you require one way ANOVA, because you are comparing more than two groups. The moment you are comparing more than two groups, you require one way ANOVA. Okay, so I'm just going to apply that. Analyze, compare means, see, it comes in the same group. We had an independent sample t-test to compare the means that comes from two different groups, two independent groups. We have used paired t-test to compare the data of same group, that is pre and post. Okay, and one way ANOVA to compare the means of three independent groups, that we are going to do. And instead of okay, I think the interest in online class is totally a rank data. So let us take weight only, not the online class for this particular comparison. Just whether this hypothesis is meaningful or not, just for the purpose of analysis, we will take weight for once. Weight, and we compare between these three groups. Designation. You getting? Dependent variable here is the weight, and we are going to compare the weight is different between these three groups, like BSc student, MSc student, and post basic student. And I'm just going to give options, and I give a descriptive. If you click descriptive and give data output, it also give mean and standard deviation of each of these subgroups. Otherwise, it will give only the p value, f value, and the p value. It will not give the mean and standard deviation for reporting. It will not give mean and standard deviation of each of the groups. So just go to these options and click descriptives. Okay, then click continue, then click OK. Then we have an output here. You see the PG students, I don't know, this data was randomly created. The PG students, there are 24 in number. Their mean weight is 58 with a standard deviation of 8.5. BSS student, there are 27. Mean weight is 55 with a standard deviation of 8.5. And post basic students, 10 students, mean is 52 with a standard deviation of 3.8. Okay, when we use the one-way ANOVA, you know, here like a t value, here it is a p value. Sorry, like a t value, it is going to be f value here. When you use ANOVA, we get f value, not the t value. The value is 1.58, which is not beyond the critical value. That's why we have the p value more than 0.05. See, p value is 0.214. This means there is no significant difference. Are you getting me? There is no significant difference between these three comparisons. Of course, it looks like difference 58, 55, and 52. But when we put into test, it does not show any difference. That means there is no significant difference between these three groups which is compared here, right? Now, if there is a significance, then you have to do a post hoc analysis. Why post hoc analysis is required? See, if you compare group 1, group 2 and group 3, okay, let us compare the one control group and experimental group 1 and experimental group 2. There are three groups you are comparing and the outcome. You find there is a significant difference. You apply a one-way ANOVA, it found there is a significant difference. The p here it is not, but if the p value is less than 0.05, that means you know there is a difference between these three groups. What does it mean if the p value is less than 0.05? The meaning is that, the interpretation is that at least one of these three groups is different from the other group. It is not necessary all three groups should be different from each other. Let us say control group, exercise therapy, diet therapy for weight reduction, for example. You have a control group, you have one group where you introduce some aerobic exercises. There is another group you introduce a diet therapy. At the end you are trying to see whether these three groups differs. When you use ANOVA and compare these three groups, you may get significant, but you don't know whether the difference is between control and exercise therapy or control and diet therapy. But if the p value is turned to be significant, less than 0.05, this means at least one comparison is significant. Either control and experimental 1 or control and experimental 2 or experimental 1 and experimental 2 are different. Any one of these should be. So for that you have to apply the post hoc test. If it is not significant, even post hoc test will not be significant in any of these comparison. How do you do that? So again the same test, go to analyze and compare means, one way ANOVA, taken this, and there is an option called post hoc. Why I initially did not do, it is not necessary if it is not significant. If it is significant, then you have to find out which comparison, which group is different from the other group. The assumption is if at least one group will be different from any of the other group. That's all. Okay. So post hoc. So there are very many different tests. Usually either we apply, depends on the distribution. There are a lot of rules about that. I don't want to go into that. Let us apply Banfaroni. Continue. Then okay. Then you get a comparison table here now. You see there is a different PG students and BSc students. The difference is 2.35 with a standard error of 2.23, and with a 95% confidence interval, the lower bound is -3 and the upper bound is 7.8, but it is not significant. You see the significance is 0.8. The p value is 0.892. That means it is not different. That means that there is no significant difference between PG students and BSc students. There is no significant difference between PG students and post-basic students, because that also the significance is less, 0.265. And if you compare, see now one comparison, two comparison, the third comparison is BSc to post-basic, BSc to post-basic. This is the BSc to post-basic. That is also not significant, almost equal. The p value is nearly 1. So this is how you apply the post hoc. Once you get significant, you will apply post hoc test to find out whether these three groups are differed in the what is the exact comparison. When is between these three groups, which group is better than the other? That's how you use. Is that clear? One way and over. Right. I think I'll move on to chi-square test now. Let us see what data is suitable for us to do a chi-square analysis here. And okay. Okay, we have two data, like one is we have a place of living urban and rural, and we have control and experimental group, right? Control and experimental group. We would like to see whether urban subjects and the rural subjects equally distributed between these two groups. Sometimes we whenever we take a control and experimental group, subjects is recruited, we want to see the homogeneity. Is there any significant difference between the control and experimental group in terms of distribution of urban and rural subjects, so that whether the groups are homogeneous or not? Or many places are used to find out association between two variables, whether smoking habit is associated with the gender. Like one side you have male and female, other side you have a smoker or non-smoker. So we'd like to see whether is there association between the smoking habit and the gender, or many other examples. Both the variable has to be categorical. That's all. The both variables which you are associating has to be categorical. Categorical means it is nominal data. Okay, only you know the frequency of it. You know how many are male, how many are female, and also you know how many are smoker and how many are non-smoker. Here in this case we have, you know how many are in control group, how many are in experimental group. In that, how many are in control group are urban and rural, how many in the experimental group are urban and rural, and you are looking for whether is there any difference in distribution. If there is any significant difference in distribution of these. For example, if there are 50 males and 50 females, okay, if I want to say that if there is no difference in smoking habit, I expect 25 males to be a smoker and 25 females to be a smoker. Then if I say, oh no, male smokes more than female, you will not agree, because out of 50, 25 male are smoker and the same proportion is there in the female. Then you get significance if there is this distribution is disproportional. Then you call it, okay, we have 50-50, 30 males were smoker, and out of 50 female only 10 were smoker. Now what do you say? These two, men smokes more than women. There is a strong association between a smoking habit and gender. You will agree with that, right? So whenever we do chi-square test, the null hypothesis is that the distribution of proportion is equal in both groups. Like in this case, what I assume for this urban and rural, the distribution of urban and rural subjects is equal in control and experimental group. That means if I have 20 urbans, 10 should be in control group, 10 should be in experimental group. If I have 30 rural, 15 should be in control group, another 15 should be experimental. That is an equal proportion. If this is the case, then I will get a chi-square value 0 and p value 1, because there is no difference in distribution, and p also I will get 1, because the probability of making, if I say there is even with this data, if I say the distribution equal, that means 20 distributed 10 and 10, 30 distributed 15 and 15. Still, if I say these two groups are different, then I am making 100% error in my judgment. That's why p value will be 1. If it is equally distributed, the moment the distribution is changing, like 10-10 I said, instead of 10-10, if it is 8 and 12, instead of 15 and 15, if it is 12 and 18, then this chi-square value will keep rising. The p value will keep coming down. At one moment, the chi-square value reach the critical point, the p value will reach 0.05. There you call, oh, these two groups are significantly different in terms of distribution of urban and rural subjects in this group. Hope you get it. So now we will apply how to do it in the SPSS. So I go to analyze. Okay. And descriptive statistics itself, I go for cross tabulation. Usually we make a cross tabulation when we do this. So I take two variables. One is controlled experimental into rows, and I take place of living into column. Go to statistics, click chi-square, and take continue. Then go to cells. Usually you take observed counts, that is enough, and percentage, usually row percentages will be better for interpretation. Then go to OK. Then this is how the table you get. So now tell me, some of you tell me the interpretation, how it looks. See, in control group, 20 subjects were urban, 5 subjects were from rural. If you look at the experimental group, 22 subjects were from urban and 14 subjects were from rural. Is it equally distributed?
No.
See, if you compare, in control group 80% of them were urban, in experimental group 61.1% of them were urban. There is some difference, but is that difference significant enough? See, we look at the significance only. You, as previous class, you cannot always accept equally distributed and the difference is always 0. If I compare one group and another group about a hemoglobin level, you may get, this group may get 10.5, this group can get maybe 10.7. This group is 10.5, the other group is 11. See, but when we apply statistics to see whether these two groups are different, the null hypothesis is 0. Null hypothesis says no difference between this group. If this group is 10.5, this group also should be 10.5. But this group is 10.5, the other group is 10.6. We will not be able to call it this group is better than this, because there is one minimal distance. So that's why we need certain critical level of difference so that these two groups are different beyond reasonable doubt. The weightage of the difference also important. That is what we want to achieve. Here you see there is a difference, 80% and 61%, other side 20 and 30. But it is towards the different, but it is not at significant, because you can see the p-value here. The p-value here is 0.162. 0.162. It is towards 0.05, but not yet reached the 0.05. If there is some more differences, you might have got significant difference. Hope you understand. If there is a equal distribution between these two groups, you will get chi-square value 0 and p-value 1. And if there is no equal distribution, the p-value start coming now. But at this case, we can conclude that there is no significant difference controlled experimental group in terms of distribution of urban and rural subjects. That means these two groups can be considered homogeneous at this point. That's all. Is that clear? Next we move on to some of the non-parametric tests. Also, yesterday I forgot to tell you how to you will make the histogram and see the normal curve, right? So we'll take any one of the variable and see graphs. Go to legacy and go for histogram. Let us check the weight variable. Okay, then you display normal curve. Display normal curve. Then click OK. Then you will get a whether this is fitting into this. That's what yesterday we have seen. This was not normally distributed when we applied the normality test. See, if this is not bell curve, you see one side it is somewhat skewed. Okay, it is a skewed data. So this is how you can check the histogram, and you can see whether it is, you can put it to the curve whether it is fit to the normal bell-shaped curve. But as it was told in the previous class, you can never expect exactly it's following a bell-shaped curve, and you can never expect that mean and median and mode is all exactly similar. We have some margin of error. That margin of error do not exceed beyond certain level. That's why we keep all these acceptable level of error. So we do some of the non-parametric tests, right? Okay. Already, whenever yesterday when I was discussing about the correlation Pearson test, I told you instead of Pearson, if you take this Spearman, it is a correlation. If the data is not normally distributed, you will apply the Spearman correlation. But apart from that, I will teach you the non-parametric. See, in analysis itself, it shows all non-parametric tests, and if it is one sample, two independent sample or related sample, or you have usually better go to legacy dialogues. If you want to apply chi-square, you can apply from here, and if you want to apply two independent sample, see, it does not even. That's what in the previous class it was discussed. Man-Whitney U test, sign the rank sum test, Friedman, all those things. You don't even know. You can play with the SPSS. You should know how many sample, how many groups you have. If you have two independent samples, go to that. If you have more than two groups, go to k independent samples. That means it can be any numbers. It can be 3, 4, 5, and two related sample and k related sample. What is the difference between these? Yesterday itself I told you, na. Two independent sample means you compare control group and experimental group. You compare male and female. You compare urban and rural. That is two independent group. When there is a that is two independent sample. Two related sample means pre-test and post-test. And K-related sample means pre-test, post-test 1, post-test 2, post-test 3, the repeated messes. Okay. Just you have to click that legacy dialog. Rest is just you are selecting what test to be applied and choosing the variable from the column. As the see whether it is parametric and non-parametric application is same here. Most important point is that you have knowledge from the previous class. Just now, an hour before, you should know where the test is up to be applicable, what are your variables, whether this test is suitable for that. Then you can apply here. You don't not necessarily to know the procedure of calculation, ranking them, taking the mean rank of it, taking finding out the sign of it, and calculating, taking an average, and comparing with the table to find out whether it is p-value is less than or more than all those. That it will do, but you must know whether it is applicable here. That's all. Okay. Now I'm going for two independent samples. So let us compare the weight of the subjects with a grouping variable like control and experimental group. Okay. So I have called a test variable, that is weight, and we want to compare between control and experimental group. That's what a grouping variable. So define group 1, and we have already coded yesterday 1 and 2, and here you see Man-Whitney U test. I'm giving OK. Then we find the result. See, here you see the mean rank. Sir, in the previous class I told no the mean rank of one group, other group. It has taken and calculated. That's all. You see the control group 25 and their mean rank is 30. How it is calculated? Actually, all the data is organized ascending order. Rank is ascend 1, 2, 3, 4, 5, 6, 7. That. Then the group is divided, keeping the same rank, and the mean rank of each group is calculated. So mean rank of control group is 30.84. The mean rank of experimental group is 31.11. So the sum of the rank is this 771, and the other group is 1120. If you do the sum of the rank divided by the n will give you the mean rank. That's all. Okay. The mean Man-Whitney U. See the Z value is 0.059. See, if it is more than 1.96, you will get the p-value significant. See here the p-value is 0.953. You are expecting that to be less than 0.05 to call these two groups are different. But the Z value, for that the Z value has to be, Z value has to be more than 1.96. But here it is only 0.059. That's why you are getting, as whenever the Z value is more, p value will be less. If the Z value is close to 0, that's why p value is close to 1. That's the relation, inverse relationship between whether it is t value or z value. The relationship is inverse. Is that clear? How do you apply here? Then analyze. About reporting, I think the previous class reduced my work. How you report the data is that always show mean and standard deviation also. Then show the median IQ. Then show the mean rank of each of the group. Then Z value and P value. That's how you will report. what output you are getting from SPSS, you cannot copy and paste the same table in your thesis and present. You have to make your own table, how it has to be reported, okay, for the scientific article, in the scientific article. Then let us move on to analyze, then non-parametric test, legacy dialog. Then we go for, we have seen two independent samples.